Exams week. Today I'm going to be introducing Unit 1, Section 1, and Section 2, pressure. So get ready. What does pressure mean? That's where we'll start today. If you've tried to hammer in a barbell into the wall, nothing would probably happen except for maybe people deciding to no longer lend you their barbells and their weights. However, if you hammer with the same force on a nail, the nail would be a lot more likely to penetrate the wall. I don't know if I indicated, but these two things are walls, just FYI. This shows that sometimes just knowing the magnitude of force isn't enough. You also have to know that the force is distributed on the surface of impact. For the nail, all the force between the wall and the nail is concentrated into the very small area on the sharp tip of the nail. So I don't know if I made this clear enough because these are certainly not to scale, but this is a nail here, and this is a barbell. Now, they're pretty much similar in size. Obviously, in real life, the nail will be much smaller, and it'll be a lot clearer, the difference in size of these two things, but apologize for the lack of scale between them. But this is a sharp nail, and then you have a barbell here, a barbell with a really wide base to it. This nail will be a lot more apt to penetrating the wall because there's a lot less surface of impact than this barbell, which has a lot of area of impact when being pounded into the wall. And then, like I was saying, the barbell on the barbell, the area touching the wall is much larger, and therefore force is much less concentrated into a specific point, which means that it's less likely to penetrate. So I kind of have these like thump, and then this one will just go straight through. So to make this concept less conceptual and more precise, pressure is defined to be the amount of force exerted per area. So that comes to the equation, I don't know, let's do a different color. That comes to the equation, so pressure equals force, or the force exerted over the area of the force, of the area of impact. So I guess, so you have your force exerted per area, and then you have your, so basically amount of force exerted, per area. Sorry, that was kind of obnoxious. So if we understand the nuances of this equation, a large amount of pressure, to create a large amount of pressure, you'd have to exert a large amount of force over a small area, or do both. A large area with a small force would yield a smaller area. So they're kind of inversely and directly related in terms of that. And this definition also means that the units of pressure are newtons per square meter, because you have your force equals your newtons, and then you have your area, because area is always squared, and the international standard SI units of area is meters. So the actual units of pressure would be newtons over meters squared, which are also known as pascals, which can also be abbreviated to a capital P and a lowercase a. So how do you find the pressure in a fluid? So we kind of went over the conceptuality of pressure in solids, and it's easier to understand this, but how do we find this in fluids? Now, a solid surface can exert pressure, but fluids, which include liquids and gases, can also exert pressure. Now, this might seem strange if you think about it, because it's hard to imagine hammering in a nail with a liquid. In general, it's hard to imagine a liquid really applying any force onto anything, because our minds are so geared to viewing things with solids and concept. And this is kind of what makes Physics 2 difficult, because it uses concepts not familiar to a lot of people conceptually. I mean, even Physics 1, the concepts you can understand in real life. Physics 2 uses a lot of unfamiliar concepts, so that's kind of just like a detracted statement I just made. But basically, to make sense of this, imagine being submerged to some depth in water. So you have you, and you're in water. The water above you will be pushing down on you because of gravity, and would therefore be exerting pressure on you. So this is kind of like the statement that I made in this area of text here. And now if you go deeper, there will be more water above you, so the weight and pressure from the water would increase as well. Now, fluids are defined as both liquids and gases, which is another unfamiliar concept to a lot of students. Now, not only can the weight of liquids exert pressure, but the weight of gases can as well. For instance, the weight of the air in our atmosphere is substantial, and we're almost always at the bottom of it. I mean, if you're on the ground, you have the entirety of the atmosphere above you. So normally, humans are at the bottom of the atmosphere and are succumbing to the entirety of its pressure. Now, the pressure exerted on your body by the weight of the atmosphere is surprisingly large. And the reason you don't notice it is because the atmospheric pressure is always there. We are born into it, we live our lives in it, we die in it. It is a constant thing in our lives, and as humans and a lot of animals have adapted to the largeness of the pressure. You really only notice a change in pressure above or below normal atmospheric pressure, like when we fly in an airplane or go underwater in a pool. So you have this line, I guess you can call this sea level or whatever you consider your ground. If you live in Colorado, that'll be a lot higher than if you're in Rhode Island. But as humans, you have your ground level, which is pretty much your ground level. This is where the atmospheric pressure is constant in human lives. You're born in it, you die in it, you're raised in it. That's basically what I said. Now, when you go in an airplane and you notice your ears popping or any uncomfortableness in your head, that is because you're noticing a change in pressure from your ground level that you lived in into a higher level. And when you go in a pool and you dive down deep to get goggles, you're also changing in pressure because you're going underneath where you consider your normal ground level atmospheric pressure. So again, your ears will feel uncomfortable, and you can notice a popping sensation or really whatever occurs with you. We aren't really harmed by the large atmospheric pressure because our body is able to exert a force outward to balance the air pressure inward. Now, if you know Newton's third law, each action has an equal and opposite reaction. That's basically our body's way of saying we are exerting a force outward to balance the force inward of pressure. So that's how we're able to deal with this pressure and how it's a part of our lives. If you know anglerfish who live in the ocean, their bodies are made to survive the extreme pressure of being deep in the ocean, where humans would just simply be crushed. They exert a different force on their surroundings, which is able to balance their structure. It's all on body mechanics, and this is kind of an interesting way to connect biology with physics. If you were to be thrown into a vacuum of outer space by some way, if you went to space and that would happen to you, your body pressure would continue pushing out with a large force, yet no air would be pushing in. And this is kind of what causes people who aren't tethered to their spacecrafts to be thrown off the space and never return, because you will simply never stop, because your body is always producing a force outward. But if you're in a vacuum of space, there's just simply no pressure exerting on you, so you're just keeping going in one direction. Okay. So the weight of a fluid can exert pressure on objects submerged in it, but how can we determine exactly how much pressure a fluid will exert? Well, consider this brick that I have in this image. This fun little brick. Again, not very scaled. You have the waves here, and you have a brick the size of the Eiffel Tower sitting amongst the ocean. But all of the information is still here. So let's pretend that we have a column that's above. Oh, this is supposed to be blue. It looks like black, so I'm going to change it to a lighter blue. Let's pretend we have a column of like air above our brick here, like a column of water. The weight of the column of water above this brick is creating pressure at the top of the brick. To figure out an expression for the pressure, we'll start with our initial definition of pressure, which is P. Give me a second. Which is P equals F over A, where P equals the force exerted at a particular area. Now, what we do a lot in physics is we do what is known as manipulating equations and deriving new equations from previous ones. So we have our equation. I'm going to use all one color here to make it simpler. We have P equals F over A, or pressure equals force over the area. Now, for the force, we should plug in the weight of the column of water above the brick. So, the weight is always found with weight equals mass times gravity. So the weight of the column of water can be written as weight equals mass of the brick, or the column of water, which is what W for water, times gravity, where obviously MW is the mass of the water column above the brick. And we can also plug this into our original pressure equation. So we can end up getting pressure equals the mass of the column of water above the brick, that's a weird W, times gravity over the area. Now at this point, it might not be obvious what to do, but we can simplify this expression by writing the mass of water in terms of the density and volume of the water. So this is where we're leaving this standardized Physics 1 stuff and moving into new variables. Density, so this is I kind of wrote my P's a little like the density symbol here. But density, I'll write a little note here. Density, gosh, it looks really similar. I'm sorry. Here, I'll put a little like boot underneath it to make it a little bit more obvious. Density equals mass times unit of volume. So mass over unit of volume. Sorry. And then we can solve this for the mass of the water column and write, so MW equals the density of the water column times the volume of the water column, because we basically manipulated this equation we had up here, where, again, PW is the density of the water, and then VW is the volume of water column above the brick. And it's not the entire volume of the pool, just of the water column. And then plugging in mass times whatever we got here into the mass of water, we can get, into the previous equation, we can get this new fun equation here. P, or pressure, equals density of the water times the volume of the water column times gravity over the particular area on the brick. Now, at first glance, this appears to have only made the formula more complex, but something magical is about to happen, you'll see. We have volume in the numerator and area in the denominator. We're going to try to cancel something here to simplify things. Now, we know the volume of a cylinder, or volume of anything really, equals the area times the height. So you have the volume of anything, which is say the water column for now, equals the area times the height. So now if you notice in the previous image, I have the height stipulated right here, kind of like a little thingamabobber. Now we can plug in this for the volume of the water to get the previous equation, and then cancel the areas to get this. Pressure equals density of the water times area times the height times gravity over the area oh my gosh, look at this. Boom, boom. The density, the pressure